So we make the statement, the speed of light in a vacuum is independent of the speed of the reference frame, and the delta t between two events depends on the velocity of the observer, and I should say relative velocities of the observers, or the relative velocity of the observers. Now let's look a little more closely. Okay? Now we've got the detector in the floor and it's emitting beeps. We still have the distance d. We're going to call this a lab. There's a lab in this ship that's going by us. And we are the observer, observing what happens to this lab. As measured in the lab, the delta t between beeps is just the distance, round trip distance 2d, divided by the velocity c of the light. However, the observer sees a different time delta t prime, between the beeps. And if delta t prime is that time, then between beeps, the lab will have moved a distance v delta t prime. Now, if we have a distance v delta t prime here, and the vertical distance remains the same, as it does, and we're not going to discuss too much about why that happens, but it's not too hard to understand. The longer path certainly implies that delta t prime is greater than delta t, as we saw before. If we look at the geometry of the situation, we see that if we have a distance delta s along here, and a distance v delta t prime here, and a distance d here, that our delta s will be the hypotenuse of a triangle whose sides are 1/2 v delta t prime and d. Hypotenuse of a right triangle with these two legs, to be more specific. The distance traveled by the light between so-called beeps is going to be 2 times this delta s. But delta s, by the Pythagorean theorem, is just equal to the square root of d squared plus the square of this expression, as indicated here. And the time required is going to be delta t prime, which is 2 delta s over c. Now, 2 delta s is the distance we travel, c is the constant speed of light. So that the delta t prime has to equal 2 times this delta s here, divided by c. 2 delta s divided by c is just going to be this expression divided by c. If we divide through by c under the square root, we're going to have to divide every factor here by c squared, and we're going to get this expression. Okay, so delta t prime is 2 times d squared over c squared plus 1/4 v squared over c squared delta t prime squared, all raised to the 1/2 power, the square root. Notice that we have delta t prime on this side and on this side. If we solve for delta t prime, we have to square both sides. We take this equation, we solve for delta t prime. By squaring both sides, we get this. And then by collecting the delta t prime terms over on the left side, factoring out the delta t prime and dividing by the factor, we end up with delta t prime equals delta t over the square root of 1 minus v squared over c squared. Now, in getting this, we made use of the fact that d is the distance as measured in the lab, and c is the speed of light. D over c is just delta t. I'm sorry, 2d over c. 2d is the time, is the round trip, c is the speed, so 2d over c is the delta t, the time it takes for the light to complete a round trip in the lab frame. Okay? Now, making use of that fact, we derive this. This tells us that the delta t that we observe as something goes by us at speed v will be the delta t that they observe divided by the square root of 1 minus v squared over c squared. Now, if v is 0, then this square root is just 1. We have 1 minus 0. If v is equal to c, well, as v approaches c, v squared over c squared approaches 1, and we're dividing by 1 minus something that approaches 1, which means that this denominator is going to approach 0. So we divide delta t by something that approaches 0, delta t prime is going to do what? It's going to approach infinity. It's going to grow beyond all bounds. Now we'll talk about what that means in a minute.